It's my pleasure to introduce our first speaker for this afternoon, Dr. Jeffry Holmes. Dr. Holmes is a professor of biomedical engineering and medicine at the University of Virginia and an American Heart Association Allen Distinguished Investigator. Jeffrey?
All right, thanks so much. As Kathy mentioned, our project is funded as a collaboration between the Paul Allen Frontiers Group and the American Heart Association. The title is Information Storage and Retrieval in the Cardiac Extracellular Matrix. So it's interesting, I was thinking about this when we were having our conversation yesterday afternoon about cell autonomous behaviors and environment, because the entire premise of our project is that much of the behavior that we're interested in heart cells is determined by the extracellular matrix that surrounds them. And there's been a lot of interesting evidence. I'm just going to show you one example emerging from the field of tissue engineering that's made us rethink all this. This is an example from Doris Taylor's group where they took a rat heart, which normally has myocytes that look like this. They decellularized it, as people tend to do with tissues these days, leaving behind just the extracellular matrix. Then they took cultured cells, in this case endothelial cells, and a myocyte-like cell line, and they perfused those back into this decellularized heart, and the cells home to the locations that they originally inhabited and assume morphologies, at least, that look quite similar to what was there before. So the endothelial cells colonize the blood vessels and line the endothelial lining, and then the muscle cells occupy the spaces that used to be occupied by the cardiomyocytes, assume an elongated shape that's similar, and start to form sarcomeres that look quite similar as well. What's even more interesting to me as somebody who studies heart disease, a disease for which the main risk factor is aging, and that we think a lot of the things we're interested in terms of cardiac dysfunction are accumulating over years and decades, is that we know that the half-life of the proteins in a myocyte is on the order of days, right? The actin and myosin that do all the contractile work turn over every week, or with a half-life of a week. So every couple of weeks, this is a completely new myocyte, except for the nucleus. They don't divide, right? On the other hand, the extracellular matrix proteins have half-lives that can be anywhere from months to years to decades in the case of elastin. So if you're looking for a place to store information that can accumulate over a long time and instruct cells differently, the extracellular matrix seems like a pretty interesting place to look. The other thing that's intriguing about this is we already know that the extracellular matrix accumulates modifications like cross-linking over a time span of decades, and that some diseases like diabetes that predispose you to heart disease accelerate the rate at which you accumulate those modifications. All right, that's a fair amount of circumstantial evidence. What's the real evidence? I think right now I would say that the real evidence is fairly sparse, and in part that's because it's only fairly recently that people have started thinking about the extracellular matrix as such an active player in what's going on in the heart. But it's also, we think, because we don't really have the techniques that we need to be able to understand that whole story. So right now, what we can do is similar to what I think many other people can do in other organ systems. So we can certainly look at the composition. We can take snapshots in time and do proteomics and get lots of good information on the composition, and people are doing that in the heart. We can look at organization through histologic techniques. This is sort of an older technique, but a nice one where this is staining scar tissue several weeks after myocardial infarction in some different animal models. And it's a Picrocereus red stain imaged under polarized light, which does a really nice job of showing you the alignment of the collagen fibers. Or we can look at turnover. This is data from Michael Kjær's group in Copenhagen, where I was on sabbatical, and they're using non-radioactive labeled amino acids to track collagen turnover in tendons, in this case, in humans. And they're getting turnover rates of fractions of a percent per hour, so something like 1% per day, which can change after bouts of intense exercise, by which I mean running a marathon. So these are all individual snapshots that you get. You can get what, you can get where, and you can get when, or more correctly, how fast. None of this tells me who, and if we're interested in the cell interaction with the extracellular matrix, that's another piece of the problem. Which cells are doing which modifications and reading which information out of the matrix? And so what we wanted to try and do for this project was to put together some of the best features to come up with to come up with a method that could tell us who, what, where, and when. I'm not going to get to when today. Our goal for the first year was to try and get who, what, and where working, and then we're going to add the labeling to this in the second year in order to be able to look at the turnover rates for the things that I'm going to show you. All right, so the technique that we're adapting here is something called spatially targeted optical microproteomics, which mercifully is also called STOMP. And showing the idea here in a little schematic. These rectangles are supposed to be myocytes. The little gray blobs here are fibroblasts. And then we threw in a couple of extracellular matrix components, collagen and proteoglycans, schematically. And really the idea here is that you can sample anything you can immunolabel. And so you put in a fluorescent tag. In this example, with the red ones I was showing, if we had a particular cell type that we're interested in, we could tag a marker on that cell type and label all of those cells. If we wanted to focus instead on a particular extracellular matrix component, we could put in a label that labels that extracellular matrix component. Once we have this labeled, then we scan through and map the locations of the labels and photo cross-link tags at those locations. So the size of the cross-linking spot is about a cubic micron. It's a little bit smaller in the depth direction. Then we pull out all the stuff we cross-linked and send that to mass spec. So it's really a sampling strategy, letting us sample for the mass spec analysis, but sample in a different way than, say, imaging mass spec, right? So then the data that I'm going to show you today, here's a couple of examples of doing this with a particular marker, alpha smooth muscle actin. All of this is going to be in 6-week-old scar tissue from a rat infarction model. And in that tissue, the alpha smooth muscle actin is most prominently expressed in a subpopulation of fibroblasts called myofibroblasts. So this is fairly zoomed in. Here's one cell. Here's part of a second one. We can make a mask from that and then go in and photo crosslink. In this case, we're crosslinking with biotin. And so you can just see all the little green spots where the biotin got crosslinked, and then an overlay to make sure that we're in the right place. If I now zoom out a little bit and show this white rectangle is the area where we were working before, not surprisingly, you see a few more cells. But I think the important point here is then we wash off the slide and you see that there's very little non-specific sticking of the biotin. The biotin is cross-linked where we want it to be cross-linked and not in other places. So that in order to analyze tissue at a volume that we need to get the sample volume we need for mass spec, what we do is go in and just delineate. So these are frozen sections. We delineate on the section the region that has tissue on it. That gets automatically tiled into a bunch of fields, and then the microscope automatically marches through and does this same operation to each of the fields. So we're going to autofocus in a plane in the center of the section, image the label. In this case, it's alpha smooth muscle actin again, make a binary. And then here we tried something a little bit different than what we'll do with some of the other labeling, which is we're really interested in picking up the pericellular matrix right at the cell matrix interface. And so in an attempt to do that, we just did a little image processing where we just dilated out and formed rings around the things that we were picking up as cells. And so what we're going to sample is that area that's right at the edges of the cell where it meets the matrix. And then as a positive control, so that all of the processing would be the same, but we would basically be comparing to what you would normally just see in a bulk analysis for 6-week scar. What we've also done in adjacent sections is to raster through the entire section and just cross-link everything. So it's like the world's slowest imaging mass spec. But we pull it out, and that way all the processing afterwards is the same so that we can do a comparison. Right now, one tissue section is an overnight run. And it takes about 6 sections to get the sampling we need for the stomp runs, less if you're cross-linking everything. All right, so then these are the results from the runs that we've done with the alpha smooth muscle actin. What I'm plotting here on the x-axis is the abundance, the number of reads we're getting in the positive control, so basically how much of this stuff is there in 6-week scar. And then what I'm plotting on the y-axis is the enrichment that we get with the stomp sampling strategy, so the pericellular sampling, compared to what happens if you take the whole scar. The two big groups of proteins that immediately popped out here are the extracellular matrix and the cytoskeleton. The extracellular matrix, one of the things that made us fairly happy when we saw this for the first time is that things that should be sorting together in the analysis basically are. This is 2 different chains of collagen 6, 2 different chains of collagen 1, 3 different subunits of laminin, so this is internally consistent. And we're picking up some of the other proteins that we expected, matricellular proteins that are associated with collagen and fibroblasts, like periostin and biglycan. But then, of course, the other thing that we picked up a lot of was cytoskeletal proteins, including things like alpha-actinin and the filamins that make me think that when we dilate it out, we probably didn't get all the way to just the pericellular matrix. It looks like what we're picking up is that edge of the cell where the cell meets the matrix. And so a little bit of refinement to do there, although sampling that region is something that we could be potentially interested in doing as well. All right, and then This is also going to give us, I think, richer snapshots, but still snapshots. We'll get information, once we add the turnover labeling to this, we'll be getting information about what different cell types are doing, how they're modifying the matrix in their environment. And then we're still going to have to integrate that to get an understanding of what's going on overall. And for doing that, we're doing agent-based modeling, which Marcus also mentioned in his talk. And the reason that we like agent-based modeling for this, I think, is probably obvious, that because you're modeling the individual cells and we're picking up a lot of information in the sampling about what each cell is doing, then this is a very natural way to integrate that information up and predict tissue structure. This example I'm showing is just a single cell type. These are fibroblasts crawling in, depositing collagen. And in this particular case, we were interested in the alignment of the collagen they deposit. And so that's what's displayed over here. All right, so I should have done this at the beginning, but to introduce the team, you've met me. This is a fun group of 4 people who had never worked together on anything before the call came out from the American Heart Association and Paul Allen Foundation. And I don't think we ever would have worked together had it not been for this project. Sarah is a microbiologist. She normally works on immune response to parasites, and she's the one who was using the STOMP technique. Eli came out of Gary Nolan's lab at Stanford and has been doing mass cytometry. One of the things that we're hoping to pull Eli into as we move forward is multiplexing this analysis, because as I told you right now, we're overnight run per tissue section. And then Sasha Klebanoff is a liposome and drug delivery guy. Collaborators, Michael Kjær, I mentioned at Copenhagen, and then Shane Pierce, who's also working on Marcus's project, and Jeff Saucerman at the University of Virginia. And with that, I'd be happy to take questions.
We have time for a question or two.
Thank you, Marcus.
I'll ask a question about the agent. So I noticed you have Shane and Jeff both in there, right?
Yep.
What's the granularity on those agents? Are they kind of rules, or are they a little more specific?
Yeah, so we've got 2 levels of them that are both better than just rules. The level of what I showed you right there, especially because we're interested in alignment, is that each fibroblast for each of its behaviors is looking up what it's going to do from fitted in vitro dose response curves. Right? So it's not just a rule. In particular with stretch, we took lots of cyclic stretching data on cyclic stretch amplitude versus cell alignment, fitted a curve through that, and the cells are just doing a lookup table to see how strongly they should align based on what the local stretch is. And we do something similar for the alignment with chemokine gradients, for contact guidance, alignment with local extracellular matrix, and then the cells are integrating that to do what they want to do. The next layer deeper, which was not in the one that I showed you, but that is under development, is with Jeff, we've built a signaling network, a model of the intracellular signaling network of all the fibrosis-related pathways. And so what we do in those versions is we swap out the fibroblast with the signaling network, and we parallel process. It's a perfect problem for parallel processing, right? Because at each step, they need to make decisions, but those decisions are based on current information in their environment, but not on interacting with one another at that time scale. And so then we're running a version where each fibroblast is a whole network.
That's awesome. Thanks.
Sure.
Okay. Thank you so much.